Our speaker is Bil Lewis. Bil Lewis of Tufts University, and he's here to talk about his magical debugger. So, take it away.
Thank you, Neil, and it is a great honor and a pleasure to be here. Is the sound good? Super. It's just after Christmas, so I ask myself the following question. If Santa Claus came down the chimney and said I could have a debugger which would give me any information I wanted whatsoever, what would I want? And I always come up with the same answer. The one thing I always want to know when I'm debugging a program is, what did the value of that variable used to be? I just want to go back in time, which of course you can't do. But if you merely record every state change in the entire run of a program, you can reproduce the world as it was. And that's what I've done. I am not the first person to think of this idea, but I am the first person to make it work effectively. So here's the idea. We are going to record events of interest. Every time that you change a variable of any sort whatsoever, local variable, instance variable, etc., array elements, every time you make a method call of any type, I'm going to record the fact that you made that method call, and here are the arguments. I claim this is a really interesting thing to do. Number one, because debugging is easier if you can go backwards in time. Number two, it eliminates all the worst problems with breakpoint debuggers. You don't have to guess where to put breakpoints. Do I put it here, there, the other place? You don't have to worry about all the extra steps, forward, skip, etc. You don't have to ever worry about the good old, how many people have done this? Whoops, I went too far. Of course. And there are no non-deterministic problems. If the problem occurs under the debugger, you've got it. It can't get away. It's also true that it gives the programmer a unique view of the program, which is kind of cool. And because all the data is serializable, you could save it to a file. You could have your customers email you the results of a debugging run, and even though they don't have the source code, they don't know what went wrong, you can take that and you can then go ahead and use it with the source code. Say, oh, there's the bug. And of course you can imagine all the other types of things you can do. When you're doing your regression testing, gee whiz, if it fails a regression test, bring it up under the debugger. It's ready the morning when you walk in to debug. Now, just a second, I need my props. Not really a bug. It's more like a snake. You see, if you know where the problem showed itself, that's like seeing the tail of a snake in the grass. And if you can grab that snake's tail, all you have to do is pull the tail, and pretty soon you get to the snake's head. And that is exactly what we're going to see. If a program outputs bad data, that's the tail. We just start with the bad data and we just go backwards. As long as you can point out, oh, that one's bad and that one's bad, which you better be able to because it's your program, then you're done. And it really is that easy. If we can't see the tail, if the program fails not by putting out something we didn't want, but rather failing to output something, that is a different type of a problem. That's not a snake in the grass problem. But it does mean that we know what we were expecting to have happen, and this is a type of bug which is much easier to debug going forward. I also have worked with complex searches over large sets of events. That is, find an event which matches some pattern. And we'll take a look at that in a moment. Now, if we can't see the tail, yes, here we are. Here's a typical pattern which merely says, this is a function call, the value of argument 0 is 0, and the method name is sort. So we go through the entire history of the program and look for a call to sort, whose first argument is 0, and we'll bring them up. Now, with breakpoint debuggers, it's not like a snake so much as it is a lizard. You see, if there is a lizard in the grass, and you grab the lizard's tail, what does the lizard do? He snaps off his tail, and he gets away, and you're left with a lizard's tail. And this is actually a very, very apt metaphor. So this is how I implemented the Omniscient Debugger in Java. I take your class files, and I instrument them while you're loading. I'm sticking my instrumentation in there. It runs in the same process as the target program, and it uses a single lock so that if you have multiple threads running, they synchronize linearly. I know how to do the same for other languages. It's just a lot harder. I've chosen these print strings. Nothing special about them. The first print string, myObject_123, is the name of the class, an iteration counter. This is the 123rd myObject that was created, and optionally, a instance variable value. So if you have myObj has a name variable, you can stick Bob in there. That's what an array of 20 integers looks like. It's the second array of integers we've identified. And then this is what a class object looks like. The string and numbers, of course, what you expect. True, false, and, because we can go back in time, double dashes if it has no value. So I would print out a person by the name of Louis, whose name, age, and home are listed as such. An array of integers, or if I go backwards in time to before Louis was created, I'll see this for the output. And we'll be seeing that in just a moment. I do method traces. I'm into method traces. I think it really makes it easier to see what your program is doing. So I do method traces that look like this, and you can see that the frob method of obj was called on obj6 and the number and the string, and it returns true. Frob called twiddle, twiddle called spin 3 times. Then you can see twiddle returned and frob returned. Because spin isn't calling anybody, I simply elide the return statement because it's pretty clear what's going on. So those are the outputs we're going to be looking at. I gave a bunch of students a problem to work with, and they did it better with my debugger than with any other method. But let's instead stop and take a tour. I have just, as you can see in the Emacs window, run the debugger, and now here. There we go. Okay. Hey, what's up, hey guys? Okay, here's what we're looking at. As we can see up here, we are now at the beginning of time. There were 1,280 events that occurred. Here are the method traces. And so from the method traces, you can see that main called print line, it made a new vector. It then called bad method, which is a static method. It then called worst method, which is also static, worst, etc. It throws a null pointer exception, which we then catch. And if we watch the code pane, we can see all of this happening. Here we are. We've just called main, so we're top of main. There we are doing a print line. We make a new vector. And now we're inside the first function, the second function, the third function. We're throwing the null pointer exception. And there we catch the null pointer exception and print out there was some bug. Underneath here, we have the output pane. And so this is what the TTY output looked like. So at this point, the only thing we've printed so far is the first line in blue. And we haven't printed out anything else, which you can tell by the double dashes on all these lines here. So I can advance through time. I can select any line here. And I will go to when that line occurred. So there we are. We're in a print line statement, like we expected. I can go back to here, and I can see there's the print line for I threw a null pointer exception. Let's take you down for a moment and look through the method traces. This is what a typical program looks like. There's a loop printing out an array, and it looks a bunch of print lines. And here I'm adding and subtracting things in a vector and stuff like that. The main bit of this program is a multi-threaded quicksort. So if we go back here, we can see in the first sorter thread the typical outline of half of quicksort, which is a call to sort, a call to average to find the pivot point. Then we go ahead and call sort recursively, doing the pivot on the pivot point. We've done the pivot on the pivot point, then we call sort recursively. We also make a new thread right there to do the other half of the sort. So this thread is sorter thread number 1, which is the next thread, and he's just like sorter thread number 2, except half the size. And the next ones get smaller and, of course, smaller. Well, more or less smaller. You can see what's going on. So over here, we have all the threads that exist in the entire run of the program, and you can see we had a dozen threads or so. I gave them names. Some are sorter threads. Some of these threads are doing other things. If we're in the middle of a thread doing some work here, we of course see the stack as we expect it to be. So there is run method, has called sort, has called average. We are in the middle of the average method. There we are. Down here we see all the local variables. In this case, we have the two parameters, start and end, but sum and I haven't been assigned yet. In the code pane, we can do step forward, just like anything else. We have step in, and we have step over, and step to the end of the entire program. Let's do a step in. And of course, you're going to see we're just going through the loop for sum, adding things up, and we're done. And of course, all the numbers over here, all of the data over there is kept up to date as we go through the program. And of course, the cool thing is we can now go backwards and we can say, oh goody, where did we come from? And we're going to see I get smaller. And of course, I goes down just like it's supposed to. We can step entirely out of this program function to where average was called in the first place. Finally, down here, we have the this object. And we see whatever values there are in the this object. For example, an array of 20 integers. If I double click on him, he will show up on this side of the display. Let me make some room. And there are all the values of the array. So let's do this. I can take the array, I can say, go to when you were created. So we go back to time 38. And of course, the array is all zeros. I can step forward saying, show me the next value of any element of the array. And you can see we're filling up the array. And if we look at that loop, that's just a typical little loop, which stores random data into the array. So I can keep going through the array. Now the array is full, and I can go forward and say, ooh, let's watch it pivot. And oh boy, I'm going to watch this array pivot. You can see wherever the asterisk is, that indicates a value which has changed between the last timestamp I was looking at and the current timestamp. So in this case, element number 13 is the only thing that changed between the previous time I was looking at and now. If I go to the end of the program, for example, I'll get lots of asterisks because everybody's changing. So we were back here. I can also do things like, hey, show me every value that element number 13 ever had. There they are. I can say, hey, cool, I want to go to when it was 1221. I select it, and I've just gone to when it got set to 1221. So this is way cool. Anything you see anywhere, you can double-click on, and it will show up over here. And if you double-click here, it opens inside itself recursively. And you can see there's a character and a byte, and oh, the same array of 20 integers. It's, yep, it's the same array. So now, let's go to the end of time and take a look at our little array over here. Everything looks copacetic. 1968 is greater than 1962, it's greater than 1775, and it works all the way down to element number 1. If we just don't look at element number 0, quicksort works fine. So what went wrong with element number 0? This actually is a non-snake in the grass problem, because what's going on is we're expecting something to have changed. It didn't change. So what we really want to do is we want to search forward to say, who was responsible for making that change and why didn't he make it? So we can do exactly that. We might want to ask the question, what were all the values that element number 1 ever had? Oh, it had the value 0. That's pretty uninteresting. And element number 0 got initialized to 1 and never changed. Okay, that's not cool. Let's figure out why. Who is responsible for changing the value of making sure that 0 and 1 had the correct values? Well, presumably the sort thread, which was the deepest. Let's see if we can find that guy. This sort thread should have sorted 0 through 19. This thread should have done 0 through 5, but he gave his responsibility over here to this guy 0 through 2, who is which sort of thread 3. Oh, clearly this guy should have taken care of it. That guy messed up. Let's go in and see why. We can step forward in time. That's what I'm going to do here. And say, well, let's see. We called sort. That's cool, and these guys are not sorted. So clearly this thread should have figured it out. Let's go ahead down to average. We can step into average. And let's go through average and see what average does. We know what it's supposed to do. It's going to take the average of elements 0, 1, and 2. And as we step through, here we can see over here, yes, the sum is changing. Everything's changing nicely. And we get up elements 0 and 1. And, oops, are we working? Yes. And we're stepping forward. And, oh, we returned the value 0. The average of 237 and 0 and 1 is 0. And of course, at this point, we can say, gee whiz, I is 2. Oh, look at that. I should have gone up so that we should have counted the element in 2. And we only added elements 0 and 1. Gee whiz, this loop right here, that should have been less than or equal to end.
This is choosing a pivot, isn't it?
So this is finding the average value so we can choose a pivot, yes.
So any pivot will still be the correct sort.
Ah, and so why didn't this? Clearly, we have to fix this first. Well, not clearly, but it seemed like a good idea, because this one's clearly wrong. You're the first person ever to notice that. Cool. But I want to talk about, look at a few other things first. One of the things I want to do is go back to the main thread and look at a few other things. The main thread came down here. After he finished doing all of his really cool quicksort stuff, he played around with a vector. Let's take a look at this vector. Go away. A vector, when I think of a vector, I think of vectors as this, some number of elements. I don't think of a vector as being an array with an index, with a change count, and all that other stuff. So I get to represent the vector the way I want to. I represent the vector as having 5 elements. And if I go backwards in time, I can say, oh, show me when element 5 wasn't there. Where did element 5 come from? Right there. We did an add of this guy into vector 0 here. And so if I can step backwards and take things out of the vector, or step forwards and see changes in the vector. Actually, this guy, if we go backwards, we see originally he was full of beer. So it looks like the program put 4 bottles of beer into the vector, and then he looks like he actually removes a couple of bottles of beer. And that's fine. Now there is a snake in the grass problem here. Let's go take a look at this puppy. If we come up to here, look at that. Caught an exception, null pointer exception. Ah, the evil null pointer exception. Actually, I love null pointer exceptions. They're so much better than segvs, you can't believe it. Why did we get a null pointer exception? This is a snake's tail if I've ever seen one. Well, let's see. Here's where we caught it. Now we're going to step backwards. And we got a null pointer exception because we called null.equals. That's pretty clearly uncool. So, null, where did this come from? S.equals, S is null. Oh, okay, well, that's clearly a problem. Where did S come from? Gee whiz, if we back up a line here, S came from this vector, vector 1. So let's take a look at vector 1 here. And we're going to get rid of this guy. And sure enough, element number 2 of vector number 1 is null. Well, where did that come from? Let's go backwards and see, that was the first time we got an element in number 2, it looks like, because we added null to the vector right there. Okay. Why did we do that? We are now in a completely different section of the program. Well, right here, we added S, a different S. S is from dt.name, dt, it's over there. So dt, are we in the right place? Just a second. We are adding null. We went back to the previous line. dt was demo thing number 2. There he is. His name is indeed null. Why is it null? Well, if we step backwards to here, he used to have a good name, Vladimir. And right there, for some unknown reason, somebody set it to null, which is actually a very common thing to do. I constantly say to myself, I'm changing this for a little while, and then I'll know that it has to be changed back to some other value. This type of thing happens a lot. And so that was a classic snake in the grass problem. You really didn't have to know the code at all to get back to this point. Let's take a look at a couple other things, and then we'll be ready for more fun. Let's get rid of you. I want demo thing. Yeah, let's bring you you can, if you want to, you can choose some point in time. Let's go back to when, let's go back to that point in time, whatever that point in time is. I think I would like to sort elements, 0, 1, 2, and 3. Actually, 1, 2, and 3 is problematic. Now, I want to go back to the program at this point in time and run a different function, or the same function with different arguments. So I am going to come down here. You'll notice in the mini buffer, I can say demo thing 0 dot sort, average, I don't want average, sort of 3 through 6. So I'm going to take the whole world, roll it back to what it looked like at this point in time, and now go forward in a separate timeline. So I'm going to retain my original timeline. I'm not going to drop any data, but I'm going to make a new world and run this function. I run it, and it should have sorted elements 3 through 6. I go through to the end of time here, elements 3 through 6. What do you know? They're sorted. And in the alternate timeline, if you really want to, you can say, gee whiz, you know, assign, I don't want 243, I want 99999. I change this to 99999, and now I can repeat my sort with 99999. And where are we? Up, and there we are. We have now correctly sorted everything. You could. I don't deal with that. It's a complication that I haven't tried to deal with. Now, this is really cool. It's really fun. It is really hard to do, and it's really kind of idiosyncratic. But who cares? It's fun. Turns out it's not actually useful. When I'm debugging a program, I find that I actually virtually never want to do this, which is a surprise. But there it is.
So the object you were there understands built from arrays. You can also recognize when you reach.
I'm sorry?
So for example, so it understands built-in arrays vectors. And so supposing you write your own class, which is some sort of collection of something, and you actually the elements.
Oh, of course.
You repeat your class.
So yes, you can build any type of display you want for it. It's it's work.
So if you make like a hash table, you won't get just the whole hash.
Let's take a look at a hash table. We are now going to go back to the original timeline. So here we are in the original timeline. And somewhere down here we have a hash table. Hash, 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 hash. Does anyone see a hash table in here? Well, I don't. So we can do a interactive search. Hash. Do you see the words hash in here? No, it doesn't like it. What? There. Hello. Man, I have no idea. Why are we slow? Okay, so here are the typical hash table. And so that's how I chose to represent a hash table. The keys being first, 0th, first, second, third, etc., and the hash values over here.
Now, did you write an alternate implementation of hash tables to get that effect?
Yeah. So basically I took the original hash table and made a subclass which would do just what I wanted in just the right way. And then I played all sorts of games to get my hash tables in where you wrote hash table. But Poof. So let's see. We do like to know when threads are dead. Occasionally we like to know, for example, if we go to the end of time, we would like to know when threads are alive. In particular, these two fine threads, named Hanger 10 and 11, they are blocked. They are blocked waiting for, respectively, demo thing 5 and demo thing 4. Gee, I wonder why. If I double-click on the two threads and say, show me these two threads, at the end of time, I see, yes, they're blocked on these things. I can open those things up, and I get to see, okay, who is blocked, waiting to get the lock? Who is blocked, waiting to get woken up? Let's see, waiters, sleepers, who owns the lock, if anybody owns the lock. So of course you can see immediately right here that, gee whiz, thread 11 is the owner of the lock for thing 5, and thread 10 is waiting for it. Thread 10 owns the lock on thing 4, and thread 11 is waiting for it. So, classic deadlock. And it's obvious, it's just like there, it's just what we wanted. I did mention the one other thing of for searching. I said that I wanted to be able to search for, show me all the calls to a function, and arg0 is equal to 0. So show me all the functions who are called with an argument of 0. And there we go. Sort is called with an argument of 0. Average is called with an argument of 0. Sort again, average again, sort again, etc. And if I don't like that, or if I want to see more, are we talking to me? There we go. And there we go. Let's only look for the ones that have sort in them, so let's get rid of average. And once again, there, no more. Sort, fine. And now we can go backwards in time. Yes? Slowly. Okay. No more debugger. Okay, that's supposed to be say and sort. I have no idea at the moment. Let's take a look at one other thing, and then it'll be a good time to think of questions. I want to go back to the top of this function, and wait a second. That didn't look right. Uh-oh. Ah, man. What do you do when you're given a talk and debugging and your debugger breaks? What? Oh, with the debugger?
Yeah.
Yeah, why didn't I think of that? Debug the debugger with the debugger. We need the debugger. And of course, as you have guessed, the debugger, everything you have been watching is running recursively under itself. This is 35,000 lines of highly integrated, beautifully crafted Java code running fully under itself, completely instrumented. Let's go ahead and start recording in the debugger. Press the button that went wrong. Get the exception thrown. We don't need the debugger. Let's look at what the debugger has to tell us about what went wrong with debugger. So, right there we have TTY output exception in debugger. Let's go look at that. Okay, in this thread, the AWT thread, boy, what a surprise, something went wrong. And let's see, what do we got? We caught an exception. We can step backwards in time to where the exception was thrown. The exception was thrown right after this returned because, looks like ts.time, gee willikers, ts is null. Bummer, where did ts come from? Oh, he's an argument to the function revert. Let's go to the caller of revert. There's where revert is called. Oh, he was just called with null. Okay, this guy still has ts. Ts is null. Ts came from here. Let's step backwards and see where ts came from in get first ts function. Here we are. This is why we got a null, because this function returns null. And obviously we didn't handle it. And so presumably the correct fix to this is to handle null when this function gives us null, or not have this function be able to return null. But that is, by and large, in essence, how omniscient debugging works. And now it's merely a question of, is it easier than sticking in breakpoints? Is it more effective? Does it do what you want? Does it work for your program? And now is a good time to take questions. Neil, you get to start.
Okay. So
Do we want him on the mic? Okay.
there's one kind of problem that doesn't occur very often, and it only occurs in certain kinds of architectures. But I have seen people write the double check for Ripon.
Oh, yes!
And, you know, if your architecture does give you a certain amount of serializability, it works just fine. When you take a debugger like this, and you synchronize all of your threads and all of their events, the bug is going to vanish in a puff of smoke. You run without the debugger and the bug is there. Sometimes you run with the debugger and the bug is gone.
Yep.
So what do I do?
So, if your bug appears under the ODB, you've got it. If it doesn't, then the ODB won't help you. And so, yes, there are some bugs that simply won't occur under the ODB. And of course, double check locking is a classic example. And it's, we can go into that in great detail. Doug Lee and Bill Pugh and I spent a lot of time on that. Different question. Yeah.
First question, how cool is that? Second question, can you comment on the class of programs which it is useful? So clearly, problems of thread interleaving are not very visible. I'm guessing also there's problems with safeness in your libraries or your kernel or so on. You're going to have a tough problem with trying to replay or go forward back in time arbitrarily.
Not particularly. Here's what I actually do. I instrument all of your code. I don't instrument the Java Foundation classes. I can, and I have done it. So, I have instrumented swing, but that means that I have to take the swing, put it into a different package, because I'm using swing here, so I can debug swing 2 underneath it, and yes, it works just fine, no problem. So there is a small class of bugs. Classically, the total store TSO style bugs, where it's a hardware issue that simply won't occur, so you can't debug them. And very little else. I've been able to find pretty much everything. Yeah.
Two questions. Do you record and play back the input output on
Yes. So for example, the TTY is basically a string. And so you could make a specialized thing like this for other streams also. And that's presumably what I would do if I had time and money and those things.
Another question was, how do you attach, or how do you launch, do you attach to
Yes. There is a question of what's possible, and then the question of what do I do? Now, what I do is I instrument code on loading. You're always running underneath the debugger. And so, for example, when we do, that's pretty much the whole story. Okay.
What sort of penalties are you seeing from the instrumentation of classes in terms of CPU utilization?
Penalties. Only if they've done anything wrong, otherwise we wouldn't penalize them. Okay. You want to know something about
Cost.
performance, huh? Where were we? This is the first time anyone has ever asked me this question today. Here we go. Answer number one. There are really three answers. Answer number one is, this is a proof of concept, I don't care. This is a good answer? Answer number two. There are bugs which are not amenable to this technique. Use another technique. I have never seen one. I have never had a bug that I haven't been able to find.
Not with this debugger, you haven't seen it.
That's true. And here's the answer you really wanted. This is a naive implementation. I can make it go faster. Number two still applies. In a 31-bit address space, I have successfully recorded 100 million events at approximately 1 microsecond per event. Caveat, caveat, caveat. There aren't very many caveats.
Just three.
In a 64-bit address space, you should be able to get a whole pile of events in there. And the question really becomes, if your program takes 10,000 years to show the bug, would you be willing to wait 1,000 years to run it under the debugger? Okay. So in particular, the worst possible loop would be this one. We are changing the value of sum on every single cycle, and we're not going out of cache. It's about 300x. If you do just a teeny bit of work, it drops by a factor of 3. If you go out of cache, like big array, boom, it drops a lot. Now we have, because you're doing more work outside, it takes longer to load the cache lines. And so just doing that makes a huge difference. Playing with strings, I don't record the internals of the string function, so boom, it's a snap. So debugging the ODB, a factor of 10 to 300. Debugging ANT, for example, about a factor of 7. So I recompiled ANT underneath ANT. It ran 7 times slower. And I was happy with that.
So can you instrument the program, when you run it, you have a log its activity, so that even when you don't have to run some of the other code signs actually fulfilled, you'll collect the log.
Wait, so, okay, I didn't quite follow. Say that again?
So you have a program which is doing this, right?
Right.
So you don't want, it's usually used by users, so you don't want to be running it actually under the debugger.
Right.
You want it to log its events and then send them to you in crashes so you can
So the question, if I followed it right, is customer is running the program, something goes wrong, can I do anything right there? No, the customer has to run it underneath the debugger. So once they do it underneath the debugger, then they can do anything.
So then theoretically, as long as you're logging all of these events, you could just put them in a file instead of...
Yes, I could just collect them forever. Basically, no, I haven't done that. It just doesn't seem to be the way to do it. But maybe I'm wrong. Maybe that's the right thing to do. I mean, you can certainly describe this as a super logging structure. It just logs everything and replays it. Different question? Yeah.
What's the granularity of the tracing?
The granularity of the tracing. Every time I see a put field in your byte file, I follow it with a record this different in my stuff. Every time I see a function call, etc. So basically everything. Like I said, I don't do the foundation classes, but I can. It's just generally not useful.
And you get local variables as well as
Yep.
so it's put field and a store and so on.
Right.
You don't need to. I guess you can reproduce those from the other events that take place in the context.
There are things that I could do which could eliminate a lot of the work that I do. This is naive in that respect. So yeah, I figure it can probably go 100 times faster.
What are your plans for making
Less naive?
Yeah, what are you going to do with this?
What I'm going to do is, I'm going to impress somebody who's going to come down and go, Bill, here's a sack of gold. And then I'll have... So the answer is, not very much right now. Right now, I'm teaching at Tufts University. I love it. I really enjoy teaching. And, yeah. And hoping that if I keep talking, someone will say, oh, that's a good idea.
Okay, but what I meant was, what's on your agenda for changing this for next month?
Changes for next month? I don't have any. You know, there are bits and pieces where I would go into this and say, oh, I want to make this change, that change, and that change. Basically, I've come to a point in the code base where the right thing to do is to take all the ideas learned, throw away all the code, start over, and do it quote unquote right. And maybe that'll happen. Yeah.
I was at a talk not too long ago, somebody giving a talk on basically this sort of idea.
Oh,
And he was talking about hardware implementation, using for threading, using the cache synchronization protocols to go how to align threads to other threads, and talking about lots of stuff.
Oh, wonderful. This wouldn't be green software, soft. Okay, I've talked to there are a number of people who are doing something in a version of hardware about this.
Track, but basically the same kind of, their thing would do checkpoints of a running process, and then you could capture checkpoints, and you could go back in time only that far, and they did.
Yes, I'm familiar with a number of people who've done a number of variations on that. Checkpoints always have the problems that now it's not reproducible. Because now you try to go forward, if it's non-deterministic, screw it. But
you can do a combination approach, right? Every time you take a checkpoint, you throw away the history. You don't want to go further back than that.
Oh yeah. Actually, this version actually has a garbage collector. I will fill it up with however many million events I want, and then I'll start throwing away old ones. Which is a really neat idea. It was really fun to do. It turns out it's not practical. It just isn't interesting. You can, because of course some of those events are useful. And in my experience, the hardest bugs I've had still fit easily within 100,000 events. It just turns out it's just not an issue. I can find ways to reduce the amount of data collected. There's so much that's not interesting. Yeah?
So I'm still a little confused about how you answer problems of state. So let's say you read from a file, and you read 1 megabyte.
Okay.
Something interesting happens, and then you read another megabyte, and then there's a program captures. And you go back to the point where you read 1 megabyte from the file, and then you want to play forward from that point. And of course, your kernel's already given you that second megabyte of your file, and you're going to ask it for a file pointer that's...
You're not executing the code.
It's not running, it's just looking at it.
All right, so remember what's happened. I've recorded everything that happened.
But you can play forward to a different
Now,
possible future by changing some parameters.
No, okay, yes, the different possible future thing is a different animal. So, so on the one side, the answer, I think you've got it then. On the one side, the answer is no, everything's history. If you want to play forward, then it gets a little bit dicey. It's fun, dicey, and like I said, it's just not useful. I just haven't found it valuable. but it's fun, because it's really fun to do. Okay, any other questions? Then I think that we will call this day a glorious success. When I finish the talk, when I gave this talk at Uppsala, I had that last slide on there. Oh yeah, And so, if you can find, I would love.
What do you mean by reproducible?
You have to be able to take the debugger, have the debug appear under the debugger. And so, in other words, if there are class loader problems, okay, that's I don't want to mess with that. I want to say you have an algorithmic problem in Java code. You're not dealing with weird stuff in hardware or anything. Anything that the debugger is designed for. If it occurs under the debugger, I can find that bug. Okay, it has been a pleasure being here.